So this is the last lesson in our third unit, and we're going to put a few different concepts together related to stoichiometry. And we're going to learn first about something called percent yield and then try a couple of calculation problems. And hopefully you'll find most of them are things that you've already seen before with stoichiometry, just the questions are a little bit different, so we'll break down how to tackle those ones, and then you should be set. So first off, we need to figure out, well, what is percent yield and why are we talking about it? So when you do an experiment, usually you're trying to produce something in chemistry. You're always trying to synthesize something. But when you actually go and collect the product that you make, there's often quite a bit less than what you would expect. There's things that you can control, and there's things that you often have no control over. So we're going to focus more on the things that we can't control, but things like human error, those are things that we could control. So if you spilled something, for example, in your experiment, obviously you wouldn't continue, you would repeat it. Um, and so on, something easy like that. But these are some things that we can't control and that are going to affect the yield or the amount that we get in the end. So there are lots more, but these are some big ones, so we'll spend a few minutes talking about those. So one, poor collection technique. So it might not necessarily mean that it's bad, it just might mean there's a better way out there. But if you don't actually have access to that equipment, then of course that's going to make your collection maybe not optimal. So for example, you could always find a more accurate electronic balance. So there's different types of balance that you could buy, and you've probably used in high school. Some have 1 decimal place. Those ones we tend to use in grade 9 or 10. In grade 11 and 12, we often use some that have 2 decimal place readings. There are some analytical balances that go 3 or more, but the price on those starts to increase dramatically in the tens of thousands of dollars sometimes. So sometimes just the way that you're measuring or collecting could be more accurate, but you might be limited by that. Other examples of collection technique may be along the way you have to transfer your samples from one container to another, and you can't get 100% of it being transferred. So those are some things. A second uncontrollable experimental error would be something to do with the purity of the chemical. Chemicals have a shelf life, they need to be stored properly. There's different grades of chemicals you can buy from chemical suppliers. And often, if we are doing an experiment in class with percent yield, you don't get 100, and some of those things come into play, but you can't control them. So making sure the chemical is 100% pure, that's hard to control. We don't always buy the most expensive chemicals. If we have an option to buy one that's a slightly lower grade to use at school to save some money, that's something that we do. Or even just sitting in the chemical prep room, even over the summer, you know, our school's not air conditioned. Even some of those chemicals can change a little bit. So purity is one that's often a factor. And if you don't have a pure sample, then when you're making your product, you're not going to get 100% of what you expect. Other things that can play a role are competing reactions or even conditions. So if your substance reacts easily in the air, in oxygen, then it's going to have a competing reaction where an oxidation is going to take place. If a different product could be produced, maybe you make a different gas, carbon dioxide instead of carbon monoxide. Or even if temperature is a big factor in your reaction, we don't have 100% temperature control in our classroom at school, or even some labs don't have 100% temperature control. So that's one thing to watch out for. So when we talk about doing experiments and error, we're thinking experimental error, things that we can't control with the conditions that we have. So how do we actually measure this? So this is where percent yield comes into play. So to measure your actual amount that you collect, we express it as a percentage. It's very, very easy to do. We just have to get some numbers. So you take the actual yield of your experiment. So this is what you collect during your experiment. So you do your experiment, you take the mass of your sample, that's your actual yield, how much you actually produced in the experiment. On the bottom, we have something called theoretical yield, and theoretical means in theory. If we were to predict how much product we would get, this would be the number. This would be something you would do a calculation with on paper. So technically all of the calculations that you've been doing so far on paper have been theoretical calculations. And when we do our calculations on paper, obviously no experimental errors at all in there. So this would give you the maximum amount that you would expect to get. So if we want to look at these terms in just a little bit more of a formal detail, the theoretical yield, the amount produced, that's determined by stoichiometry. So stoichiometry calculations on paper and in 100% perfect conditions where there's absolutely no errors. Whereas your actual yield is the amount of product that's actually produced in a chemical reaction measured after you do the experiment in the lab setting. So we're going to try out some problems where we're going to calculate the percent yield. Now the nice thing is once you figure out how to tackle these problems, the percent yield calculation is actually the only new part of the question. All of the other parts are based on stoichiometry and involve things like limiting reactants, which we've already learned. So once you figure out what to do with the question, if you were comfortable doing stoichiometry and limiting reactant types of questions, then you should be set. So let's try out a problem together. We'll walk through it. I'll get you set up. And then I think once you see what it's all about, then we'll be able to try it out together. So you've got 20 grams of bromic acid reacted with excess hydrogen bromide, and we want to find out two things. What's the theoretical yield of bromine, and what's the percent yield of bromine if 47.3 grams is produced? So let's walk through these parts here and see what we've got. So first thing, you've got a mass of bromic acid, which is 20 grams. And then it says you've got excess hydrogen bromide. Even though they don't give us a number, write it down. This is important. Excess means you've got lots of it. Do you remember limiting and excess reactants? Here, since they're saying this is an excess, they're also secretly telling us that our other reactant must be the limiting reactant. So here we don't actually need to go through a limiting reactant calculation to answer our problem. They're telling us already which one the limiting reactant is, even though it's not explicitly stated. Okay, now let's look at part A and part B. So part A asks for the theoretical yield of bromine. What it really says is, well, if I did this calculation on paper, what would the mass of bromine be? So for part A, we want to find out that mass of bromine. Now, part B, we're not going to get to quite yet, but let's take a look at it while we're here. So, part B says 47.3 grams of bromine is produced. What's the percent yield of bromine? So, let's write up part B's information here with bromine. We want to find out the percent yield of bromine. That we don't know. But this number here, 47.3, this is the actual yield. It's saying this is how much was produced, which means we're assuming this was produced in an experiment. So for part B, we have the mass of our actual yield already, and this is 47.3 grams. So we're going to keep that in mind for part B. But let's go back and answer part A. To find percent yield, we need theoretical yield. And this mass here is what we need. So how do we do this? This is where the stoichiometry comes in. You have the mass of one compound. You need to find the mass of another compound. Even though they're calling it something different here, theoretical yield, we're just finding the mass. Can I change the mass of my HbRO3 into a mass of bromine that would be produced? Sure, we're just going to use our three-step process like we've been doing for solving stoichiometry problems. So, what's step one? Always change your mass into moles. So moles of HbRO3. And we know between mass and moles, we need to use molar mass. And this is going to be for HbRO3. Once you've got your moles of your reactant, we need to find moles of our product, which is bromine. We know when we go from moles of one compound to another, this is where your mole ratio comes in. Once you've done your mole ratio and find your moles of bromine, just like before, third step, we need to find the mass of the bromine, but this time remember, use the molar mass of bromine because that's what we want the mass of. So now that we've mapped that out, hopefully you can see once we've broken down some of those new terms, theoretical yield, percent yield, you can see that part A, everything all here in blue, those three steps are the same three steps that you've done with other stoichiometry problems. So what I want you to do now is pause the video and see if you can complete those three steps on your own. And then once you've given that a shot and some practice, unpause the video and we'll walk through the answer together. So now what we're going to do is walk through these three steps that we mapped out to find the mass of bromine, the theoretical yield. So let's start looking at those. Step one, we needed to find out the number of moles of HbRO3. We take the mass, divide it by its molar mass, and we get around 0.155 moles. Next, we need to do our mole ratio step. They're not 1-to-1 ratio. If you look in your balanced equation, it's 1-to-3. 1 mole of HbRO3 to 3 moles of bromine. So 0.155 times 3 divided by 1, and we'll get about 0.465 moles of bromine. Now that we've done our mole ratio step, we can move on to finding the mass. What's the mass of our bromine? So step 3, take our moles, multiply it by the molar mass, and we're going to get a value. It should round to 3 significant digits, which is 74.3. This number here is our theoretical yield. in perfect conditions on paper, we've calculated that you should get about 74.3 grams of bromine produced. If there's no errors, if everything goes 100% according to plan, that's what we would expect to get. So that's the answer to part A. Now, we've got our theoretical yield. Let's just go back up to the question to revisit part B, and then we'll take a look at that answer. So, in part B, we need to find the percent yield. If you remember from what our percent yield formula is, we need the actual yield divided by the theoretical yield times 100%. We have the theoretical yield, 47.3, and we just calculated the theoretical yield in part A. So now we have the two values we need to calculate percent yield. So again, since this is new, I want you to try and pause the video, do your percent yield calculation, and when you're ready to check, we'll take a look at the answer. So now we're going to take a look at the answer for part B. So first of all, make sure you've got your formula in there. Actual yield over theoretical yield times 100%. These are where our values are going to come in. 47.3 grams, our actual yield. We calculated 74.3 grams theoretical yield. And you should get about 63.7% for your for your percent yield. So what that means is you do the experiment and you only get 63.7% of what was expected. You've lost that other remaining percentage along the way due to whatever errors are occurring. We don't know specifically here because we don't have details about the experiment, but it could be a variety of different reasons for that to be happening. Okay, now let's try out another problem and see how you do. This one's just a little bit harder. In this question, we've got a reaction between zinc sulfide, oxygen gas, and it's producing zinc oxide and sulfur dioxide. So we've got a balanced equation here. Let's just start adding in information that we have as we read. So first part of the question says we have 16.73 grams of zinc sulfide. So let's record that. And it's reacting with 6.70 grams of oxygen gas. Okay. Then it says if 8.94 grams of zinc oxide are actually produced, that's a key word, determine the percent yield of this reaction. So how much is actually produced means that for zinc oxide, this number here, the 8.94 grams, that's our actual yield. You do the experiment and you get 8.94 grams produced. And we want to find out what's the percent yield of this reaction. Since they're giving us the actual yield for zinc oxide, that means we're going to need to find the percent yield of zinc oxide. And remember, when we're calculating percent yield, we need our actual yield over theoretical and multiply it by 100. So in this question, we're given our actual yield, but we need to find the theoretical yield. So how are we going to find the theoretical yield? Well, we're going to have to do some stoichiometry to do that. But this question's a little bit trickier. So taking a look at what we've got down here, we've got masses this time of both reactants. The last question, we were given the mass of one and told the other was in excess. So right away we could figure out which one the limiting reactant is. But guess what? This time we don't. Which one of these is your limiting reactant? We don't know. So we've got to figure that out. So for this problem, there's a couple of steps. First step, find the limiting reactant. Is it zinc sulfide or is it oxygen? Do your calculation. But we didn't have to do that in the previous question. Once you know which one your limiting reactant is, then you can go ahead and say, okay, I'm going to use that to find out my theoretical yield. Even though it's not explicitly said here, we need our theoretical yield. That's missing. So, step 2 here, we're going to find the mass of zinc oxide produced. And this is our theoretical yield. And this is going to be using stoichiometry. So step 2 is like the same steps that we just did previously. Once we know the limiting reactant, we've got it in moles, we can find the moles of our zinc oxide and then find the mass of our zinc oxide. Then the very, very last step here, once you've got both, then you can find the percent yield of zinc oxide. So, since now we've tried some problems, and you should know how to find limiting reactant, and you know your stoichiometry, you try and pause the video here and try the question out. See if you can find first the limiting reactant, then find the theoretical yield, the mass of zinc oxide, and then finally the percent yield. And we'll walk through those 3 steps together. So hopefully you've had a chance to at least start solving a problem. We're going to start with the first part, finding the limiting reactant. So remember, when you find the limiting reactant, we need to find the moles of both of our reactants, and we're going to divide by the balanced equation coefficients. And whichever number is smaller is going to give us our limiting reactant. So let's take a look at what's happened here. So in blue, we've got our mass divided by molar mass to get our moles of both reactants. Zinc sulfide is 0.171, and oxygen gives us 0.209 moles. When we divide by the balanced equation coefficients, there's a 2 in front of zinc, so we divide it by 2. There's a 3 in front of oxygen, we divide it by 3. And when we look, which is the smaller number, the oxygen is. So that tells us oxygen is our limiting reactant. So now that we know our limiting reactant, we can move on to step 2. Using our stoichiometry roadmap, change the number of moles of oxygen, this number up here, the one that's highlighted, into moles of zinc oxide and then the mass. So if you haven't tried this part of the problem yet, pause, see if you can do those few steps. If you're ready to check, we're going to move on to that part of the answer next. So once we know which one our limiting reactant is, we can set up our balanced equation again. So it will show the remaining stoichiometry steps that we need. This is our balanced equation. We know that oxygen's our limiting reactant, so we have to use it to find out the mass of zinc oxide. we started with 6.70 grams, but we've already done that calculation where we found the number of moles of oxygen, which was 0.209. And now we have two remaining steps left. Find the moles for zinc oxide using our mole ratio, and then back into mass. So we look at the ratio, it's 3 moles of oxygen for every 2 moles of zinc oxide. So in our mole ratio step, we need to make sure that we don't forget those values there. So when we do that, and I just realized I've got a typo in here, so let's fix this. This is oxygen. So we take our moles of oxygen and multiply them by a ratio 2/3, and we should get about 0.1393 moles of zinc oxide. Once we've got that, then we can get our mass of zinc oxide, which is 11.4 grams. Once we've done this step, we can move on to percent yield. This number here is our theoretical yield. So if you haven't tried the percent yield, again, pause the video here and we'll walk through that last step together. So very last step to this problem, it's a long one. Let's find the percent yield. So percent yield is our actual over theoretical and multiply that by 100. So in the question, they told us our actual yield was 8.94. If you don't remember that number, you can scroll back up to the question to take a look. We divide that by our actual yield, or sorry, theoretical yield, which we just found. Multiply that by 100. And then we get approximately 78.4%. So this is telling us that when this experiment was conducted, we got 78.4% of the product that we expected. The rest of it was lost due to whatever experimental error that was encountered. So if you're finding that you can do percent yield questions quite comfortably, then you've mastered quite a few different techniques and ways to do calculations in our unit. So if these are good for you, great. If you're finding them a little bit more challenging, they also can be, because it puts a lot of concepts back together that you've learned throughout the unit. So just keep practicing, ask more questions, and post them online.